And well, this is what we did last time, last Tuesday. You remember that this is a single, well, this is a single line diagram, electric diagram. And the only thing we need to understand is that can be a distribution board. If it's a single family house, it's quite simple. We only need to divide this into different circuits. Um, and what is the criteria? Well, if we have lights, all lights should be on the same circuit. If we have sockets, all sockets will be on the same circuit. And then depending on the power of the appliances that we are connecting, we might connect different things. It depends if it's a three-phase circuit, a single-phase circuit. If it's a single phase and we are working with the American system, with the US system, you know that we can have 120 volts between the line, the neutral, or we can have 240 between two lines. Okay, so that depends on the power. As a rule of thumb, I love rule of thumbs. So we can say that we can use a single phase if the power is up to let's say 2000 watts, the electrical power, and we are using single phase with 120 volts. Okay, if the power is up to 220 watts, we can use a single phase with 120 volts. So we have to connect the neutral and the line. If we increase the power, we can have single phase with 240. That means that we have to connect two lines so that we can have 240. If the power is up to, let's say, 10,000. Okay. And if the power is above 10,000, I would use a triple phase to 240. Okay, so if we are dealing with a single family house, usually we have this, depending on the single family house. Okay, that there are single family houses with elevators and crazy things. But if we are designing single family houses with 2-3 bedrooms, this would be enough. So we have to figure out how to divide our circuits into circuits that have less than 2000 watts. If we have a single phase, this can be a small public building. Okay, so if we have the devices up to 10,000 watts, and when we have a public building with an electric heating or cooling system, it's very likely that we can have 5,000, 6,000 watts. Then we can work with a single phase, but some of the circuits should be 240 volts. And when we are above this, okay, so when we have circuits, we have mechanical equipment, we have elevators, we have those chillers or not boilers, electric heaters, whatever. But if something is above 2,000, 10,000 watts, we should use a triple phase diagram. This is serious, okay? So I wouldn't design a triple phase electric installation. Single phases we can. I mean, it's like calculating the structure of a 2-floor building. We should be able to do that because it's something. We're not doing crazy things like huge overhangs or whatever. Up to 2-3 floors, we should calculate everything: the mechanical systems, the structural systems, and even the electricity. If we are in a large building with different uses and different pieces of equipment, then we can rely on electrical engineers. Okay, But this is like a rule of thumb. Okay, so you can learn this. In most of the single family houses, uh, we are doing this. So we have to calculate the appliances that we have. We have to calculate the power, and then we have to create different circuits up to 2000 watts. Okay, so we can connect all the lights together. This is one circuit. We can connect all the sockets together. That's another circuit. Except if we have sockets for the refrigerator, because a refrigerator it's usually close to 1000 watts, or the electrical, yeah, the electric kitchen, yeah, it would be close to 2000 watts. Okay, so we can have a circuit for all the close or all the sockets, other than the electric heater or the electric kitchen. Okay, but anyway, and if some of the appliances is close to 10,000 watts, from 2000 to 5000 watts, okay, then we can use a single phase, but then we have to connect these two lines, line one, line two, so that the tension is 240 volts. Okay. So as a rule of thumb, we can take this, and today what are we going to do? Okay, so we are going to calculate, especially the circuit breaker. Uh, we are going to we have to be able to do something like that, like a single line diagram. As architects, this is all we have to know for single family houses, for small buildings. If they are large buildings, it's a question of scale. Okay, so it's a question of dividing the building into different sectors, and then there will be distribution boards for each sector. When we have a public building with 2 floors, usually we have a distribution board for the first floor and another one for the second floor. If the building is too long, is very long, like imagine the TDS building, then we can divide different rooms or different sectors. In the TDS building, we have, for example, the wood shop. In the wood shop, there is a lot of equipment. So probably we will have a distribution board only for the wood shop. Okay. And then for lighting, we can have another circuit. But if it's too, if there is a lot of power in this circuit, then we can divide this into three. So we can have a light circuit for the second floor, the CAD lab and the studio. Then we can have another light circuit um, for the offices, and then another light circuit for the regular classrooms that are not the computer lab or the studio. Okay, and at the end we have to divide this. If we don't want to complicate things, we have to divide circuits into different circuits that don't have more than 2000 watts. Okay, but it's a question of creating different sectors and apply the common sense. Okay, so does it make any sense that all the electrical lighting of the classrooms in the TDS building are in the same circuit? It makes sense. Does it make sense that one of the machines in the wood shop is connected to the same circuit than the lighting of the bathroom? No, it doesn't make any sense. Okay, so it's just common sense. And then it's a question of, okay, if I want to use just a single phase, so we have to divide this into circuits no more than 2000. If I want a single phase connecting two lines with 240 volts, I can divide this into circuits like this. And if I have this kind of equipment, like the elevator or probably the electric heaters that we have in the TDS center, then I need a triple phase installation. Okay, and then we have to rely on electrical engineers. So we are going to work on something very simple. So let's work with building with these three circuits. Okay, so we have lighting for common areas. We have 15 LED light bulbs with 40 watt each, and we want to connect this to a single phase 120. We have an electric boiler, and that electric boiler is 5000 watts. So we want a single phase, but with 240. And then we have general power sockets. We calculate that the total power of these sockets, it's around 1000 watts. So we need a single phase circuit with 120 volts. How do I know this? Well, I need to know the appliances. If I'm working with the computer lab, imagine that we are working with the sockets of the computer lab. What is the power of electric power of a computer? Good question, but I'm sure we can find out. Okay, so here this mini desktop uses 15 watts. This is 5 to 8 watts. Okay, so how much electricity does my computer use? And this is in the specification of the equipment itself. Okay, so we can deal with the company. Yeah, I think this is 300 watts. It's yeah, it's the maximum wattage. Yeah, so this is the maximum. So we can have up to 300 watts for computers, including the unit and the screen, maybe. Okay. So then we need to know how many computers we have in that room, multiply times this, and well, this is the size of our. If we need one phase, we need two phases, then we need three phases, then we need to calculate that. Okay, but those numbers are in the specifications of the equipment that we need. Okay, so if we are designing a classroom or a computer lab, okay, so how many positions, how many computers are there in the computer lab? This is, it's not our decision. We have to deal with our client. In King State College, we have 16 or 18, I don't remember. Okay, so this is it. Why? Because our client wants this computer lab with 18 computers, okay, 18 times 300 watts. So this is the total power of this room. And I think it makes sense that this computer lab, because in the computer lab, we have more electric power in sockets than in other classrooms. In other classrooms, yeah, we can have power, but most likely we won't have 18 computers running at the same time. Anyway, those are questions that we have to ask ourselves, our clients, and then we need to divide this into different circuits. Okay, so it's not easy, it's not complicated, it's easy, but I think it's about experience. So once you have designed a couple of electrical installations, you should be able to do it. Okay, don't worry, I'll take the attendance at the end of the class again. So if you are late, don't worry. Where were we? Okay, there you go. So this is the building, or this is the part of the building that we are designing. So first, we have to calculate circuit breakers. Okay, so we have the three circuits here. So the first circuit is lighting. Lighting is 15 LED or LED light bulbs times 40 watts. So this is 15 times 40, 600. 600 watts. 600 watts. With this rule of thumb, up to 2000, we can use single phase 120. Okay. What can we do here? Well, it's always the same formula. You know that power equals tension times intensity times power factor. We can say that the power factor, what was a typical value of a power factor? Someone remember? Hello? Does someone remember the typical value of a power factor?
I don't know.
Okay, so it's the lesson is posted there, and the power factor usually it's between zero 0.8, 0.9, something like that. Okay, so let's say that the power factor is around 0.8. Um, let's do this. So what do we have to calculate now? We have to calculate the intensity. Okay, so we have to solve the intensity because the circuit breakers, the units are amperes. Okay, so we need to calculate the intensity. So the intensity is the power divided by the tension times the power factor. Okay, what is the power? 600 watts. What is the tension? 120, because this is what we have decided. The tension is 120 single phase, and the power factor is 0.8. This 0.8, by the way, has to be within the brackets. So how much is this? It's 600 divided by 120 divided by 0.8. Okay, so this is 6.25 watt amperes. So what is this circuit breaker? If you remember, I told you that commercial circuit breakers are these. We have 10, 16, 20, 25, 35, 40. Okay, so if our maximum intensity is 6, then the circuit breaker should be 10 amperes. There you go. Okay. Second, the circuit is the electric boiler. We have 5,000 watts. So how can we calculate this? If the power is 5,000 watts, then we know that the intensity, the formula is always the same. So intensity is power divided by tension and power factor. So our power is 5,000. The tension in this case, it's 240 because we have decided, we have this rule of thumb. So between 2,000 and 10,000, if we are using a single phase, the tension, it's better if it's 240 times 0.8. So this is 5,000 divided by 240 divided by 0.8. Okay, so this is 26.04. Then the circuit breaker should be more than 26. So let's say, I think there are 30, well, I don't know, let's say 35. Okay, and finally, number 3, we have power sockets. So we can have the same formula. The power is 1,000 divided by, up to 1,000 we can have 120. So this is 120 times 0.8. So this is 0.8. 1,000 divided by 120 divided by 0.8. Okay, good. 1,000 divided by 120 divided by 0.8. Okay, it's 10.4. So the circuit breaker should be 16 because it has to be more than 10. 16. Okay, a piece of cake. And then if you want to draw a single line diagram, and in architecture, we have to do this. So we should be able to work with this single line diagram. So I'm going to do someone very quickly now. Okay, so this is always like this. No, I don't want arrows here. Okay, what are these two elements? Okay, we'll talk about this later. But as you know here, we have three circuits. We have 1, 2, and 3. Okay, so here we need 1, 2, and 3. And each circuit has a circuit breaker. Okay, so the circuit breaker will be here. What is the symbol for this? Well, we can use, do we have something here for circuit breakers? No, we don't. Okay, so let's do it. Okay, so circuit breaker, usually it's like two circles, two tiny circles, and then a line that is tilted here. So it's like a switch. Okay, so when this line is not connected here, so that means that there is no electricity. If this goes this way, then we have electricity. Okay, so this is the symbol for a circuit breaker. So we can copy this here and this here. Okay, and now we need to type the values. So this is 16 amperes, this one. The other one was 35. And this one is 10. Okay, very simple. And here we can type the name and the power of the circuit. So this is lights, and the power of this circuit was 600 watts. The next one was the electric boiler with 5,000. And the last one was the power sockets, 1,000. Okay, quite easy. Those are the circuit breakers. And then you remember that in we had like three different elements. We have these miniature circuit breakers for each circuit. We have only three. Then we have the RCD, which is the differential circuit breaker that detects or is a protection against different intensities in the line and the neutral. And then we have the main switch, okay? Okay, so this is what we are representing here. So this is the differential circuit breaker, and this is the main switch. We can copy the same symbol here, but in this case, this is the differential circuit breaker. So for the differential, you see that we have two figures here. We have the amperes, and then we have milliamperes. This is the intensity. This is the difference of intensity that makes this switch to be disconnected. Okay, and so the main intensity has to be the highest here. So we have a circuit with 25 amperes. So this differential breaker should be at least 25. And then this is the sensitivity, or the, yeah, so what is the difference between the line and the neutral that makes this disconnect? So usually it's always 30 milliamperes. Okay, so with this, if we have this 35, so that is 35, and then dash 30 milliamperes. Okay, so those are the requirements of this differential breaker. And finally, we have this one, which is the, what was the name of this? Yeah, the main switch. I forgot it. This is the main switch. Okay, in this case, this is a single phase. We don't have any triple phase or three-phase circuit, so everything is a single phase. If we want to give even more information about this, we can have a color code. So we can have a line. Let's say we have the color code here. Okay, so lines are brown, black, and gray. The neutral is the blue, and this is the, usually we don't, we take for granted that there will be an earthing circuit, okay? But in this single line diagram, we don't represent the earthing, so we take it for granted. So if we have the blue one, this is the neutral. And then we have two lines because it's the American system. So this is line one, can be brown. And then line two. And it can be either gray or black, say gray. Okay, and now we want to make it perfect. If we have a single phase with 120, we can have two circuits here. So this is the neutral and line one, so, or line two. Okay, so this is the neutral line in line two. This is the neutral and line two as well. And the electric boiler, we can say that is line one and line two. Okay, if we want to make it perfect, now we understand everything. Here, it's a single line diagram, but we know that we have to connect two wires. So here we are connecting the neutral in one of the lines, here we are connecting two lines because this is the maximum power, and we want 240. And here we are connecting the neutral and another line because the tension has to be 120. Okay. So this is all we need to know. I mean, we need to analyze the power, we need to analyze the devices that we have in our building, and then if it's a single family house and we want to go to a single phase, everything is easier, it's cheaper, but the triple phase, it's more reliable and it's safer. Okay, so it's more expensive. So then you have to deal with your client. Probably there's a, in the municipality or in the building codes or regulations, okay, up to, if you have your house up to 10, usually it's always 10,000 watts. It's like a limit. Then from 10,000 to 25,000, then you have okay, but then you have to deal with the electric company. Because this is something that we don't do as architects, but our clients, they need to sign a contract with the electric company, and then they have to declare how much electricity they need. Okay, so it's something that they should know beforehand. It depends on if, especially if we have electric heating and cooling systems, then you have to go to from 10,000, above 10,000. If you are not using heaters or air conditioning, probably you can be below 10,000. And depending on your power, your maximum power, you will have to pay more. Okay, so calculating this beforehand, it's important, not from the architectural point of view, but it is important because it depends on what our client is going to pay. And probably they don't know anything. They don't know the consumption of a heater or of an air conditioning system. If they don't know that, at least we should understand that they can have the lowest the lowest bill if they don't have electric heating and cooling systems. If they do have electric and cooling systems, probably they might need the triple phase, and they will need to increase the maximum power, and they need to declare this to the. So although we don't calculate this, or we are not supposed to calculate this, but at least having a rough understanding of what our client is going to need, it's useful because they will trust us. They are not, our clients are not dealing with the electric engineers. They are dealing either with the architect or with the constructor. They are not dealing with electrical engineers. Things are becoming more complicated because we depend on electricity. Now, 20 years ago, nobody had a mobile phone. Now everybody's having a phone, and nobody had a computer. Now we all have different computers and different tablets, and so things are getting more and more complicated in electrical systems. So this is the first conversation with our clients. Okay, what kind of house do you want? And then if you want to integrate the PV panels, that makes it more complicated. Okay, so, but at least this rough estimation of, okay, do you need a single phase system or a three-phase system? That depends especially of the heating and cooling. If you include electrical heating and cooling, you would need a three-phase system. And then what is the maximum power that you need to declare to the company? That's another relevant question that we should be able to ask in the design process. But for a simple example, this is all you need to know. Okay, so how many circuits we have, if we need 120 or 240, if we need a single phase or a triple phase, and the size of circuit breakers. If we know this basic information, then we can go ahead with a single family house. Are we done? No, because now we have to calculate the money. So we need financial cost considerations. Okay, so let's use this example. As you can see, we have three circuits. This one, this one, and this one. Okay, so this is power, but now we need to turn power into energy and eventually into money, because this is what our client will understand. They might not understand watts and kilowatt hours or whatever, but they do understand dollars. So this is what we are going to do now. So if we have this circuit, 6,600 watts, now we need to estimate time, because now we need to turn power into energy. So we need to multiply by time. So how many hours a day do we use the lights? 10 hours? 10 hours per day. Okay. So how many hours a day do we use the electric boiler? If it's summer, probably we don't need an electric boiler. But the coldest day in winter, how long can we use this? 10 hours, 12 hours, 24 hours? I don't know. Let's say 12 hours per day. And then the power sockets, well, first we need to understand, okay, if we have computers, we have, I don't know, computers, a printer, whatever. How long do we use this per day? Computers, I don't know, 5 hours, the TV, I don't know. So just make a rough estimation. So let's say 6 hours a day. Okay, so now we are turning power into energy. So that would be 6,000 watts per day. That would be 5,000 times 12,000 times 12, 60,000. This is 6,000. And power socket, 6 hours time. So this is 60,000 units. Watt hours, sorry, it's not watts. So we have watts times hours. So it watt hours per day. So those are the units. As you know, the unit that we use, it's the kilowatt hour. Okay, so we have to divide this by 1,000. So 6,000 watt hours is 6 kilowatt hour per day. Uh, 60,000 is 60 kilowatt hour per day, and 6,000 again, it's 6 kilowatt hours per day. We are not the electricity bill is not we don't know the electricity bill on a daily basis. We have monthly electricity bills, so we have to multiply this times 30 days, and that will be 6 times 30. It's 180 units kilowatt hour per month. That would be yeah, it's 60 times 30 days. The total will be 1,800, and this is the same because it's 6 kilowatt hours. Okay, so what is the total? What is the total monthly consumption? 180 plus, what is plus? 1800 plus 180. So this is it. Plus 180 plus 1800. 2100 to 160 kilowatt hours per month. Okay, and now what about the money? We have to go to this slide here. Now this is the consumption. This is what we can do, and now the money doesn't depend on us. Well, it depends the amount of energy that we need. The price of energy depends on the state, depends on the company, so we don't know. Okay, we agreed that the electricity here, it's in the United States, quite cheap. It's cheaper than in crazy countries like in Denmark or in Germany, where they pay a lot of taxes. They are happy. So, but I think the average is like 10 cents. Well, here in New Hampshire, let's do this in New Hampshire. So in New Hampshire, it's 16.5 cents per kilowatt hours. Okay, so now we have to go down. And if this is the total energy consumption, times 0.165 cent, or no, dollars per kilowatt hour. So how many dollars? 2160 times 0.165, $356. Okay, so that would be the electricity bill of our client. Well, we are in winter. We are using this electric boiler 12 hours a day. Okay, so probably in July, we don't consume this. I don't know if we have a air conditioning. Yeah, and then we need to know the power of the air conditioning system and how many hours a day we are using this. Okay, if we are working with the PV with PV panels, for example, with the PV array, and we are in a zero energy building, our client is saving around $356 per month. And now it's a question, okay, how much money do I have to pay up front? And then if I have a zero energy building, this electricity bill is for free. So I'm saving this every month. Now, what is the cost of this PV array with the inverters, with the batteries? If I need batteries, what is that cost? I don't know, $30,000. Okay, $30,000. So if it costs $30,000, let's say, divided by 356. So my rate of return, my return of investment, this is a technical, so it's 30,000 divided by 356 is 84 months, around 7 years. Okay, So that's why this is important. We are committed to sustainability. We want to save the planet. We want to design zero energy buildings. But at the end, if it's not a good business, forget about it, because nobody will do that. So this 7 years, this is the ROI. So that stands for return of. Okay, so this is a return of investment, ROI. It's much more complicated, okay, because there is a formula, and if you are studying business or something like that, probably this is one of the first formulas that you can learn. It's more complicated because we have inflation. It's not included here, so it depends on how the value of the money in 7 years. Will it be the same because of the inflation? Will it be? We don't know. I'm not an expert on economics. If I were, probably I would be happier now, but I'm not. But this is just a rough estimation. Maybe it's not 7 years, it's 8 years or 6 years and 6 months. We don't know, but I know that it's going to be around 7 years. That depends on the price of energy. If the price of energy it's increasing, we have done this with this price. But what if in a couple of years there's another crisis that we can't even foresee, and the price of the energy goes up? We don't know. Or what if it goes down? If the price of energy goes down, then the return of investment will be longer. But if the price of the energy goes up, then we can return that investment faster. Okay, so there are things that we can't. There are things that we don't know, and we can't even foresee. Well, we have data. We know what has happened. So if we know that over the last 20 years, the price of the energy has going up or has going down, then we can foresee what's going to happen in the next 20 years. But we don't know. Anyway, so this is it. First, we need to calculate. So this is theory. We need to calculate the circuit breaker. Okay, so because without those circuit breakers, there will be a likelihood of a disaster in our electrical installation. So we need to dimension this depending on the power that we have in each circuit. Then once we have done this and we know the power, then we can calculate the energy. And this is the total monthly energy consumption. This is interesting because we can calculate the money, the electricity bill that our client is going to pay. And then if we want to design a PV system, a PV array, photovoltaic system, okay, so we can inform our clients about this return of investment. If it's less than 10 years, everybody will accept it. 10 years is a good, it's like a magical number. More than 10 years, it's where will I be in 10 years? Will I be alive? I don't know. But I don't know why, but 10 years, it's something. Okay, I can imagine myself in 9 years and 11 months, but I can't imagine myself in 11 years. I don't know why, but it's true. So 10 years, it's like a psychological threshold. So are we done? Not yet. Just a few things more. The goal we are dealing with first. You remember that we calculated the power of our systems, the boiler, the chiller, the power in the heating loads in winter and summer. We use this, okay? And then I remember that I told you that it's important understand the concept of COP, the coefficient of performance, okay? Because this coefficient of performance is the value or the parameter that turns thermal energy into electric energy. Okay. And this is what I want to do right now. We will do that next week as well. But I want to introduce this because if you have worked with this Excel file, most of you have done this. So here we have the heating load. You remember that we can have the full occupancy or we can have a schedule. Anyway, if you have this chart, and this is 1 day, okay? So this is from 0 to 24 hours, but this is the electric consumption in 1 day. How can we use this to dimension our electrical system? If we are using an electric heater or an electric chiller, this is what we are doing in the TDS center. The TDS center, we don't have boilers, we don't burn any fuel, everything is electric. And nowadays, the future is electric. I don't know, maybe in a couple of years, I change my mind. But nowadays, with the development of PV panels and PV arrays, buildings are getting ready to be 100% electric or to run on electricity. And then we will stop burning fuels. Okay, so this is what I can, well, it's not just me. So this is what experts are predicting, that buildings are tend to be electric buildings like the TDS center. Okay, so if we have done this, we have to look at this column and we have to look at the maximum value that we have here. Okay, so in this column, the maximum power is 257,208. This is BTU hours. Okay, we are talking about power. So I think this is the biggest or the highest figure, 257,208. Let's write down 257,208. This is BTU hours. If we are working with electricity, we need to turn this into watts. So we can go to a converter, BTU to watts. So the maximum was 257,208. Okay, so this is the power in watts. So it's 7,538 watts. Now we have to deal with the COP. Okay, so the COP, the coefficient of performance, is the parameter that turns thermal energy into electric energy. So if our thermal energy was, we have just calculated 75,380 watts. What is the electric value? Or what is the electricity that we are actually using? Okay, so the electricity we are actually using is the thermal power divided by the COP. Can somebody tell me a usual value for a COP of a heat pump?
Wasn't it like 0.9 or like 1?
0.9 or 1? No. Okay, so there's a lesson on COP and EER. Okay, so if we are dealing with air-to-air systems from 2 to 3, air-to-water, ground source heat pumps up to 6. Okay, we're using COP. We're not using the EER because the EER, it's BTU divided by watts. I don't like this figure. So we're dividing watts and watts. Okay, so we're dividing the same units. So it can be 2, 3, if we are dealing with an air-to-air system, 2.5 to 4. Okay, so let's say that the COP is 3 in our system, is 3. So the total electric consumption will be the thermal consumption, which is 75,380 divided by 3. So 75, 380 divided by 3, it's 25,126 watts. Okay, if our heating or cooling system, the power of our heating and cooling system is not the BTU, it's not 75 watts, we have to divide by the COP, by the COP. So this is the actual electricity that we need. So if this machine or this heat pump, it's good, we need this electricity to provide this thermal power. Okay, so if we are having 25,000 watts, what kind of system do you think we can use? A single phase system? It's just yes or no. So you have 50% of getting the right answer. What do you think?
No.
No. Why? Why?
It's over 10,000.
It's over 10,000. Yes. Okay. So according to this rule of thumb, if it's above or over, it's above, let's say over 10,000, then we need a triple phase system. It makes sense because we were calculating a public building. When we were dealing with this, we were not calculating a single family house. We were calculating a building with 100. Yeah, so the occupancy was 120 people. We don't have 120 people in single family houses, at least not in my house. Okay, so that makes sense. This is not a power for a single phase system. It's a triple phase system. And this is only the heating. Then we will have lights. There will, okay, so that's something serious. And it's out of our, so it's not as simple as this. So we need to divide this into different circuits, and we need three phase. Probably we need different boards. If the building is too big, we will need a transformation station, as I showed you here. Okay, so if the building is, we need a transformer substation in our building. Okay, so architects, we are not doing these kind of things, but at least we need to know what kind of building we are designing. Okay, so are we designing a simple building in which we can solve everything with a single phase diagram? If we are not doing this, okay, so we need an electrical engineer. Okay, so by this time, this quiz should be available. So you can start doing it. And okay, so we have 9 questions. I don't know why we don't have 10. Okay, but we have 9 questions. The first and the second questions are the same exercise that we did on Tuesday. So it's on the lesson. You don't have any excuse. This question 3, from question 3 to question 8, it's about the calculating circuit breakers. Okay, and then the question 9, it's like a summary. So this is what we have just done. We have 1, 2, 3, 4, 5, 6 different circuits. The powers are here. So this is the electric heat pump. So this is the electric heat pump is this one. Okay, so you have to go over the power that we need in, so question 8 is about circuit 6. Question 7, it's about the circuit 5. Question 6, it's circuit 4. Okay, so you have here the power. You have here the hours a day that we are using all these circuits. And this is the price of electricity. So this is a European price. It's not a United States price. Okay, 20 cents, something serious. So go ahead. You have like 30 or 45 minutes to complete this quiz. I'm available. If you need any questions, just ask me and I'll be with you.